I had asked my colleagues to teach in my absence. I hope you can hear me.
Yes, ma'am.
Yeah. So now we are moving to chapter number 29. And chapter number 29 is on the electrical properties of materials. Okay. So first of all, we have to answer the question, what is the meaning of electrical properties of materials? Electrical properties of material simply means how a material will behave in an applied electric field. When you apply an external electric field, how is the material going to behave? So that's the meaning of electrical properties. So electrical properties of materials will include both static and dynamics. Whatever you had studied till now, it was all static. So static is also included. Dynamics also will come under electrical properties of materials. And the next thing is, based on electrical properties, you can actually classify materials into the following categories. One would be conductors, insulators. Insulators also, you can use another word for insulators, that is dielectrics. Okay. And then, of course, you have semiconductor and finally superconductors. Now, when you look at how this classification has been done, this classification has been done based on what is the room temperature resistivity of a material. I hope you know the difference between resistance and resistivity. Resistance is going to have the unit ohm, whereas resistivity will have the unit ohm meter. Okay, and what is the relationship between them? Anyone? Rho equal to R A by L. If I'm talking about a wire, A is the area of cross section, L is the length, and R is the resistance. And please remember, resistance is going to depend on the size of the material that you are taking, whereas resistivity is the property of the material. It doesn't depend on the size of the material. If you're taking copper, for example, at room temperature, it is going to have a certain resistivity. It doesn't depend on whether you're taking a wire or a plate or whatever it is. Okay, so the classification of electrical properties, is based on the room temperature resistivity. Conductors, as the name itself suggests, will have very good electrical conductivity. Okay, and by the by, conductivity and resistivity are reciprocals of each other. Okay, conductivity is 1 by resistivity. So conductors will have a good conductivity, or if you look at the resistivity, we are going to talk in terms of resistivity, you will find that the resistivity is going to be very small for conductors. It's about 10 to the power of minus 7 ohm meter at room temperature. Whereas when you're talking of insulators, they don't conduct electricity, so their resistivity will be very, very high, 10 to the power of 5 and above. Okay, and between these two categories lies what is called semiconductor. I'm sure you must have studied semiconductors also in your +2, silicon, germanium. Then you must have talked about the P-type semiconductors, N-type semiconductors, and you know there is something called doping. If you add a trivalent impurity, then you get a trivalent impurity will give you what kind of a semiconductor? Anyone here? Trivalent will give you N or P type?
N type, ma'am.
N type. Everybody agrees? Okay. So your semiconductors are going to be something between the two. You will find that if I have to talk in terms of the resistivity, you will find that the resistivity will be lying between 10 to the power of minus 5 to 10 to the power of 5 at room temperature. And then, of course, superconductors are not really a part of this, but then we would like to just mention them also in this discussion. One sec. I don't know why everybody needs permission to be admitted. See, this is the problem. Samyukta, this is the last time I am allowing you. Please don't use your Gmail IDs from next class. I will not let anyone enter with your Gmail IDs. Okay, so now coming to superconductors. Superconductors are actually not really a part of these things because the superconducting behavior is something that you are going to see below what is called a critical temperature. Okay, above that temperature, most of the time they behave like semiconductors. Most of the time they behave like semiconductors. So superconductors are a category of materials which show a special property. If I am going to plot resistivity versus temperature, you find that there is a certain temperature called the critical temperature, And below that temperature, the resistivity will be 0. Below that temperature, the resistivity will be 0, okay, and abruptly it rises to some high value, and then from there it may be a constant, or it may be a semiconductor, or it may be a conductor, but whatever it is, it shows non-zero resistivity at temperatures above critical temperature, and below critical temperature, the resistivity abruptly becomes 0. Okay, so these are superconductors. Next, what decides the classification of these materials? What decides whether a material is going to be a semiconductor or a superconductor? See, I'm not going to allow anyone. I'm just going to deny entry because it's outside IFHE. Okay. Electrical property is determined by what decides whether something is a conductor or a semiconductor or dielectric. Okay. So these things are decided by the following things. First is, what is the value of the electrical field that you are applying? Sometimes what happens is, no, a material may be a dielectric or an insulator for a certain value of field that you are applying. But when you apply a large field, what happens is it breaks down and becomes a conductor. I'll give you an example for this. Air normally doesn't conduct. Will you all agree with me?
Yes, ma'am.
Right. Air doesn't conduct, especially when the air is dry. Okay. Now, what happens is when there is a lightning, what happens is the fields involved are so large that they start ionizing the air molecules. Or what happens is they just knock out electrons from these air molecules, and such a surge of electrons will be there. So through that, there will be a conduction happening. So what happens is, what is normally a dielectric or an insulator now becomes a conductor. Another example that you must have all, did you all have workshop? Okay, I'm so sad. I feel so sad for you because you are all doing everything sitting at home. Actually, there is one aspect of workshop called welding. Okay, when you're doing a welding, you have a plate to weld and you have the electrode. So when you bring the electrode, what happens is the gap between the electrode and the plate becomes so small, and there is an electric field involved. Okay, so there is a conduction that will happen because of the large electric field. That gap of air becomes a conductor. So you see that happening, and you don't have to go to the workshop. I'm sure that you must have seen when you are traveling somewhere also, you must have seen those sparks coming. Okay, that's because of the conduction that is happening in air. So electric field value is one thing that decides whether a material is a conductor or not. Next thing, intrinsically also, a material to a certain extent decides whether it is a conductor or an insulator or a semiconductor. For example, copper. The copper molecule, the copper atom, the number of free electrons that it is able to contribute. It is able to contribute free electrons. Therefore, it is going to become a conductor. Okay, so the behavior of the individual atoms, the electronic configuration, or when they form a molecule, whether it is going to be a dipole, whether it is not a dipole, all these things, basically the behavior of the individual atoms or molecules also will decide whether a material is a conductor or not. Next, we can talk about interaction between materials, the kind of bonding that may be there between these atoms or molecules. Those also will decide whether a material is going to be a conductor or not. Those of you who you all studied chemistry, so you obviously know about the kind of bonding that can be there. Okay, so these bonds also will decide what kind of a material you're going to have. Like, for example, if you have a metallic bonding, then it's a conductor. You have all those free electrons just floating around, not localized to any given atom. So they participate in conduction. Similarly, as we go along, you're going to see that some molecules will behave like dipoles. They will behave like dipoles. Like, for example, water molecule behaves like a dipole. So these dipoles, two neighboring dipoles can interact with each other. So those interactions also will decide the electrical property of material. Now, at this stage, it is too premature for me to make you understand it. But as we go along, you will understand. Next is conditions like temperature. Like certain materials, I'm talking about a metal, for example. If I could cool the metal down to 0 Kelvin, 0 Kelvin is an impossible temperature, but then if you cool the material to 0 Kelvin, then that metal will not conduct anymore. It will become an insulator. So conditions like metal also will decide the electrical properties. And I'm sure you all know that when you heat a material, its resistance actually let me not even discuss that. Basically, just right now understand that temperature is one of the factors that decides the electrical property. Okay. Now let's just go ahead and go to general characteristics of these class of materials, let us say. As I have been mentioning, I think already twice I mentioned, conductors are going to be materials which are going to have free electrons. They will have free electrons if I'm talking of metals. Okay, but then sometimes you must remember that conductors can also be, let's say, electrolytic solutions. Electrolytic solutions, like for example, Na plus and Cl minus is what you're going to find in salt solution. So there, what will conduct is the ions themselves will be conducting. Okay, so if any material is going to have free electron, or if it is going to have mobile charges which can move, then those class of materials are conductors. Now let's come to insulators. As I said again, insulators are also called dielectrics, and the properties of these are going to be decided by polarization. Already we have studied a bit about polarization in chapter number 26. Okay, how certain materials exhibit a polarization behavior. They behave like dipoles. Okay, so the polarization also decides the insulator property. Okay, so in insulator, like for example, I'll talk about, you all know that bits of paper, if you take a comb and then, rub it on your shampooed hair and then bring it near bits of papers, you know that the bits of papers will get attracted. So here what happens is, there is a dipole formation. The bits of papers would start aligning themselves, dipoles will align, and then there is no actual movement of charges. There are no moving charges, but dipole formation will be there. And these dipoles are responsible for that attraction. We will see that a little later. Now coming to semiconductors, again, I already mentioned, there are two types of semiconductors, N-type and P-type semiconductors. N-type semiconductors, the person answered wrong. N-type semiconductors will have pentavalent dopants, 5 electrons. Pentavalent dopants will be there. Electrons will be the majority carriers. Whereas P-type materials will have trivalent dopants. Holes will be the majority carriers. Please remember, holes and electrons, the difference is in their mass and the difference is also in the sign of the charge. Okay, and the basic intrinsic semiconductors can be silicon and germanium. So by doing a doping, you can actually increase the conductivity of these semiconductors. Now let's go to superconductors. This again I mentioned, below the critical temperature, you will find that there is going to be no conduction. I mean, there is going to be no resistivity. Resistivity becomes 0. In the last chapter, you studied potential difference and things like that. Okay, so here what happens is, if you take any 2 point, let us say this is my superconductor, if I take 2 points on the superconductor, there will be no potential drop between those 2 points. Potential difference will be 0. That is when it is in the superconducting state. And how are these materials different from your conductors? The difference lies in the formation of what are called Cooper pairs. You know that normally an electron and another electron will repel each other. They don't attract. Okay. But then in the case of superconductors, there is a mechanism which is really outside the purview of your studies, but I'm just mentioning. Okay. What happens is 2 electrons actually form a pair. There is something called electron lattice interaction, they call it. So 2 electrons, though normally they should be repelling, they form a pair and form what is called a Cooper pair. Now these Cooper pairs are actually the ones which will carry the current in the material, and there is no resistance. Okay, now coming to polarization. I mentioned the word polarization in the context of dielectrics. So please remember, some materials are naturally polarizing. Like for example, water is a dipole. Water is a dipole. Whether you apply field or don't apply field, it is a dipole. But certain materials are not dipoles. They become polarized. I gave you the example of the paper, for example. They become polarized when you apply an electric field. And what happens is the polarization will be directly proportional to the amount of electric field that you're going to apply. And those class of materials are called linear dielectrics. Okay, and what happens is, or maybe I'll just explain like this. Let's say that you have your positive nucleus, and around that you have your electrons. You have your electrons. Now you can treat the positive part as a point charge. You can treat it as a point charge located at the center of the nucleus. Similarly, the electron cloud can also be treated as a point charge. Let's say the center of this charge is here. So you can find that both these are coinciding with each other. Both are coinciding with each other. So these kind of materials, if they coincide, will not be dipoles. Will not be dipoles. But in certain type of materials, what happens is, when you're going to apply an external electric field, what happens is, you know that electrons will experience a force anti-parallel to the electric field you're applying. Anti-parallel to the electric field you're applying, and positive charges will experience a force in the direction of the electric field. Okay, so what happens is, what you will finally find after you apply the electric field is that the positive part of the atom, the positive will move slightly to the right in the direction of the electric field, and the negative cloud will go like this, or the center of that will be here. Okay, or there is a displacement between the center of the negative charges and the positive charges, and this process is called polarization. This process is called polarization. And how much it displaces is going to depend on the electric field. So these kind of materials where the polarization, do you remember the expression for the dipole moment, anyone? P is equal to? Charge multiplied by the separation. Charge multiplied by the separation. So now you see here, if D is the separation, okay, you can see that separation will be proportional to the field that you are applying, or the dipole moment will be proportional to the field that you are applying. All such materials where this happens are called linear dielectrics. And think of what will happen if I keep on increasing the field. I keep on increasing the field. The dipole cannot keep extending like this forever. What happens is, some of the electrons at least will now get enough energy to just walk out of this particular atom. They just get knocked out. That's called the ionization energy. So they are able to get sufficient energy, and they're just getting able to come out of the atom. Once they come out of the atom, what happens? What you're left will be a positive ion and the free electrons. Okay, now this process by which a dielectric or an insulator becomes a conductor is called breakdown. That's called breakdown. I just gave you the example of air becoming a conductor. That's also a breakdown. This process by which you apply a large electric field, and so large that the atom in the dielectric gets ionized. Ionized means it breaks down. It becomes a positive ion and free electron. So once free electrons are there, these electrons can move. The ions can move. So what happens is the dielectric now becomes a conductor. This process is called a breakdown. Okay, and please remember, different dielectrics have different breakdown values. Different dielectric have different breakdown values. That is, there is a certain maximum electric field that it can withstand. It can withstand a certain maximum electric field that you are going to apply. Beyond that, if you increase the electric field, then it breaks down. Okay, so it also signifies the strength of the dielectric, how much it's able to withstand. Okay, therefore, you talk about a quantity, you talk about something called the dielectric strength. The dielectric strength. So dielectric strength is the maximum electric field that the dielectric can withstand. It's a maximum electric field that it can withstand. If you cross that value, then it breaks down. It is no longer a dielectric. Okay, now air. I told you about breakdown of air. Air will break down if you're going to apply a field 10 to the power of 6 volts per meter. Then it breaks down. Or if I'm talking about plastics, for example, it will have a value 10 to the power of 7 volts per meter. So different materials will have different dielectric strength. Dielectric strength is the maximum electric field it can take. What is normally if I ask you to write the unit of electric field, what would you write? Electric field unit. My God.
Newtons per coulomb.
Newton per coulomb. Very good. That is one person said. Newton per coulomb is a unit of field. Okay. Now remember, volts per meter is also a unit of field. This volts per unit you were introduced in the last chapter. I hope you remember the relationship between electric field and potential difference. Anyone remembers? E, V, and D. Anyone remembers?
E is equals to minus dV by ds.
Right. Minus delta V by delta D or ds, whatever. Okay. So it is coming from here. This unit of electric field is coming from here. Volts per meter. Okay. So what normally happens in this breakdown is, if the material is thin, let's see, what is the meaning of volt per meter? 10 to the power of 6 volt per meter means if I have a meter thick layer of air, if I have a meter thick layer of air, and if I put a potential difference of 10 to the power of 6 between these two ends, it will break down. That's what it means. Now what happens? Instead of 1 meter thick, if I have a small thickness, let's say 1 mm, do I require 10 to the power of 6 volts? The thickness of the air that I'm talking about is just 1 mm. Will I require 10 to the power of 6 volts?
No, ma'am.
No. I require about 10 to the power of 3 volts per mm. That's all will be required. Okay, so that means the thickness of the material is the dielectric strength is the same. That is an electric field. That is the same. But then how much voltage it can take is going to be decided by the thickness. So that's the reason why sometimes, I don't know whether you've noticed it. I don't know. This generation, I don't think anyone has even seen that, because all of you are using these iron boxes or this press, the box that you use for pressing your clothes. They are all ready-made boxes. Once it doesn't work, you just throw it off. But you ask your parents and see, they will talk about iron. The name iron came because the box itself was made of iron, very heavy. Okay. And in my grandfather's time, it was, they used to put charcoal inside that. Even now, if you go to Adobe, he will put charcoal. Okay, but then we started using the electric iron. So in the electric iron, what happens is, if you see inside, has anyone seen an electric iron and what is inside an electric iron? Anyone here? You will find what is called mica sheets. Mica sheets. Okay, mica sheets are shiny things. Mica is a very good conductor of heat and a very bad conductor of electricity. Very bad conductor of electricity. So what is done inside the iron box, even the modern iron box, what happens is, there will be filaments through which you're going to pass the current. And that heats. That heat has to come to the body of the iron box. How does it come? This mica sheet will conduct the heat, but it doesn't conduct electricity. Because it doesn't conduct electricity, what happens is you will be protected from shock. You won't get a shock. Because it's not going to conduct electricity from the filament to your body of the iron box, but it conducts heat very nicely. Mica is also a dielectric. It's an insulator. It's a dielectric. But then what happens is you will have thin flakes of mica. Thin flakes of mica. So sometimes what happened, a small voltage some kind of a shorting happens. A small voltage is sufficient for that mica to just burn and then for the iron box to just conk off. This is not going to be asked in an examination, but these kind of examples you will remember all your life. That's the reason why I'm telling you that. Okay, now let us go to the electrical properties and let us study static conditions. First, we are going to see static conditions of a conductor. Okay, we are going to look at a conductor and how a conductor behaves when you apply an external electric field, and this in the static condition. Static means, static means the charges finally go and take some positions, they remain at rest, and everything is constant after that. So we are going to study the static condition. So for that, what you do is, let us consider a rectangular block of a metal, like rectangular block of metal. And as we all know, they have lot of charges which can move. The electrons can move. They are free electrons. So let's take such a block. Let's look at the figure A. Let's take a block, a rectangular block of the material, and put it in an external uniform electric field. Let's put it in a uniform external electric field, E0. Let E0 be the external electric field that you are applying. What did I tell you will happen to the mobile charges when you apply an electric field? I said F is equal to Q into the electric field that you are applying. So what will happen? The negative charges, the free electrons, will all start experiencing a force opposite to the direction of the electric field. They will experience a force opposite in direction to the direction of the applied field. The field in the picture is in the downward direction. Therefore, the free electrons will all start moving to the top. So in a short time, when I say short time, I'm talking about around 10 to the power of minus 9 seconds. In this short time, what happens is there will be an accumulation of negative charges at the top on one face of the material. On one face of the block, there will be an accumulation of negative charges, and on the opposite side, there is a deficiency of electrons. On one side, there is an accumulation of electrons. On the other side, there is a deficiency of electrons. And please remember, the entire material is neutral. Equal number of electrons and protons are only there. So if a certain amount Q goes to the top, a certain amount minus Q. If a certain amount minus Q goes to the top, the deficiency at the bottom will be plus Q. Okay, so there will be an accumulation of positive charge of the same magnitude on the opposite face. Please remember, I'm talking about a disk. I'm talking about a rectangular block. So one side becomes negatively charged, the other side becomes positively charged. Equal and opposite charge. So when I say equal and opposite charge, you must immediately remember your insulator or sheet of charge. Sheet of charge. So this process by which these charges have got separated and gone to the two faces, this is happening because of actual movement of charges, and this process is also called polarization. This is also called polarization. So there is a polarization happening. So charges are, in society also, when we talk about certain parties, we say they polarize the society. They polarize the society on the basis of language. They polarize the society on the basis of religion. Some parties polarize people on the basis of caste. So what is the meaning of polarization? They separate people based on caste or religion and then form groups. Same thing is happening here. The material gets polarized. There is a separation of the some part of the electrons and the protons, and they form two sheets. Okay, and now what happens is, because they behave like two sheets, each of them will give rise to a field. Each of them will give rise to a field. Okay, now there is a field because of the negative charge. There will be a field in the, it will be towards it. Okay, so I will call it E prime minus. And because of the positive charge, there will be a field away from positive. Away from positive, that also will have the same value. That will also have the same value. So I will call it as E prime plus. Okay, so each of them will contribute sigma by 2 epsilon naught. Already we have studied in Gauss law. Sigma by 2 epsilon naught will come because of the negative plate. Sigma by 2 epsilon naught will come because of the positive plate. So the sum of these two will be equal to sigma by epsilon naught. Okay, so between the two plates, between these two faces of the conductor, now there is a field that is created. This field is E prime. This field is E prime. E prime is the sum of the field due to the positive and the negative charges. That's called E prime. And this E prime is called induced field. It is called the induced field. Why are they called induced field? Again, go to chapter 28, your Gauss law. There you have studied charges get induced on the surface. Okay, so the same. That's what is happening here. These charges, because they moved like that, they are called induced charges, and because of them, there is a field set up in between. It's called the induced field, and the induced field will be E prime. And look at the direction of the induced field. The induced field is in this direction. In this direction, applied field is in this direction. Applied field is in this direction, and the induced field is in the opposite direction. So now what happens inside the material is the resultant field that you will have inside the field is coming because of the principle of superposition. The net field inside the material will be E equal to vector sum of E naught plus E prime. Vector sum of E naught and E prime. E prime. And what happens is the two of them will be equal and opposite. E naught and E prime will be equal and opposite. Therefore, the net field inside the material becomes 0. The net field inside the material becomes 0. That is because now the question that some of you may be having is, how much charge will go to the two surfaces? How much charge will go to the two surfaces? Enough charge will go to the two surfaces so that sigma by epsilon naught becomes exactly equal to E naught. And it will be in the opposite direction, so that the net field inside the material is 0. Have you in the past seen some situation where the net field inside a material was 0? Gauss law. Do you remember Gauss law? Hey, are you all there or gone?
Yes, ma'am.
Yeah. There you have seen that if I have a material and if there is a charge on it, then I told you that the charges will quickly go and occupy the surface so that the inside will have electric field 0. Like that only here. You are not putting any extra charge, but then because of the electric field that you have applied, electric field lines are going inside the material. Electric field lines that you have applied are all in the material. They are inside the material that the material will not like. So what will it do? It sets up its own induced field and opposes the applied field. So therefore, the net field inside the material becomes 0. And this condition is called electrostatic condition. This condition is an electrostatic state. Okay, so inside the body of the material, now there is no electric field. And those two charges which got separated, the negative charge and the positive charge, will go and sit on the surface, and they don't move after that. They don't move. Okay, or it is a static condition. What about the field outside? The field outside will be the same E naught that you applied. So you will find that electric field will be there perpendicular to the surface, and it will be 90 degrees to the surface, and it is there outside. Okay, but then inside the material, the field got cancelled out. And this happened because of the induced charges. Okay, so this is how electrostatic equilibrium is achieved by metals. Here I have taken a rectangular block. What if it is not a rectangular block? What if it's not a rectangular block? Look at this. I have an odd shaped metal. I have an odd shaped metal piece. Okay. Now, if I put this in a uniform electric field, so initially what will happen? It will be like this. Initially, the applied field that you have, the field you have applied is E naught. Okay. And then You are taking this piece of metal and then putting it inside it. So what should happen? What should happen to the free electrons? Free electrons will all start drifting in the direction opposite to the electric field. And there is a deficiency on the other side. So within a short time, what will happen? There will be an accumulation of electrons on this side, and there will be positive charge, equal and opposite positive charge on the other side. Okay, so that's what you're seeing here. And here what happens, because of these induced charges, there will be an electric field. What will be that electric field? That electric field will be E prime, which will be exactly opposite to E naught. Therefore, inside the body of the material, the next picture will show you that there is no field inside. There is no field inside. Net field is 0. But outside, what will happen? That will be slightly different from what you have seen in the previous picture. Outside, what happens is the field will be E naught. You applied E naught, all right. So therefore, the field will be E naught, but it will be uniform field only far away from the material. Far away from the material, you will find that the field is uniform. How am I saying that from the picture, that the field is uniform? What do you find here? These lines are all parallel and equispaced. Yes or no?
Yes, ma'am.
But look at what is happening near the material. Near the material, you're finding that the field inside is 0, but outside there is a field, non-zero field. But the field will be perpendicular to the surface at every point. The field will be perpendicular to the surface at every point. And because the shape of the material is not a straight line, therefore the field lines also here will not be straight lines. It will be curved. It will be curved. But then as you go away, it will become E naught. Okay. And in the last chapter, I didn't teach you that chapter, but in the last chapter, you have seen that equipotential surfaces are always perpendicular to the electric field at every point. Yes or no? Yeah. So because of that, you look at the equipotential surface. You look at the equipotential surface here. The entire body of the material is an equipotential. Everywhere inside and outside, it's an equipotential. And you can see the shape of the equipotential is the same as the shape of the metal object. But as you move away, the shape changes and finally becomes a plane. Finally becomes a plane when you are moving away. Okay. And can I ask you a question? I didn't teach you, but I just want to know whether you have an answer. Why did I say that the entire metal, the entire conductor is equipotential? That is, the potential inside is the same as the potential on the surface. Why did I say that? Madam or sir has definitely taught you this. The entire conductor at electrostatic equilibrium is at the same potential. Can you prove what I just said? At least now can you say? Sometime back you also D is equal to minus dV by dr. Change in potential with distance with a negative sign is electric field. If the electric field is 0 inside, what will you say about dV? What will be change in potential between 2 points?
0.
0. That means every point of that conductor has the same potential value. So that explains why the electric field is 0 inside. And then the next question, what if the electric field was not 0? If the electric field was not 0, you would have again seen movement of charges. Because still you have more charges inside, no? But you're not going to see anything like that. It is electrostatic. So that also goes on to say that the electric field inside is 0. So this is how electrostatic equilibrium is achieved. But then the difference between a rectangular block and this is that you will find that the surface charge density of the induced charges will not be the same at every point. Wherever the radius of curvature, I hope you know what's the radius of curvature. For a plane, what is the radius of curvature? For a plane, what's the radius of curvature? Anyone? Or for a lens, what is the meaning of radius of curvature? Anyone? What's the radius of curvature of a lens? Yeah. What's the meaning of radius of curvature? Nobody is able to answer this. Okay. If I have a lens like this, the radius of curvature is the radius of the imaginary sphere from which the radius of this imaginary sphere from which this lens is cut out. Now, do you remember what is radius of curvature?
Yes, ma'am.
Yeah. Okay. So think of this. What will be the radius of curvature of the surface? It will be infinity, because this has to be cut out from an infinitely large sphere. So the radius of curvature, that there is no curvature there. So the radius of curvature is infinity. Okay, so with this in mind, let's just come back here. You're seeing that different parts of this conductor are having different values of radius of curvature. Like for example, if I see this portion, it is having a small radius of curvature. So wherever the radius of curvature is small, there you find more accumulation of charges. Do you remember lightning arrestor and all that you must have studied in your school days? Sharp end. Go man. Am I teaching school children here? You don't remember anything that you studied in school. Okay, so charge concentration will be more in sharp edges. Sharp edges are points where the radius of curvature is small. So that's something that you're seeing here. And at every point inside, the electric field is zero. Outside, the electric field is non-zero. But everywhere on the surface, the electric field is normal, makes a 90 degrees with the surface. So that's also one reason why this is electrostatic. Okay, now let's, so just to complete. So the electric field is perpendicular to the conducting surface everywhere. That's why it is statics. And you find that far away from the conductor, the electric field is uniform. Okay, and near it, it is not uniform as the picture itself shows. Therefore, the equipotential surfaces are also not planes. They are curves. They get distorted. And the entire conductor is an equipotential. So quickly, can someone sequence everything that I told you on this odd shape material? So what's the first thing? You're going to take this metal and put it in a uniform electric field. Then what happens? What happens? There is a charge separation. Induced charges are formed on the two surfaces. And these induced charges will give rise to an induced electric field. This induced electric field will cancel out the applied electric field inside. But outside also, please, this point also I forgot to tell you, outside also there is an addition of fields. There is a superposition of fields. So that is the reason why this distortion is there. Okay, so it is not the applied field that you're seeing here. It is a sum of the applied field and the field because of this positive surface. Similarly here. And then what did I say? Electric field inside becomes zero, but outside the electric field will be normal to the surface, and the electrostatic potentials also will be distorted, and the entire body of the material is at the same potential. Okay, so I think I'll just stop statics here. From next class, what we are going to see is dynamics. Dynamics means there will be continuous motion. It doesn't take 10 to the power of minus 9 seconds and then go and settle somewhere and after that doesn't move. No, that's not going to happen. Now we are going to see dynamic conditions. In dynamic conditions, there will be continuous flow of charges. Like for example, your electricity. Electricity is simply flow of charges. It's a continuous flow of charges. So we start with dynamics in the next class. Any doubts? Did you all attend the classes which were conducted by sir and madam? Because it is only trust. Even here, I know many of you are happily coming and just logging in and going and sleeping or watching something. You are adults. There is only so much we can do. Okay, so you are paying, I am getting my salary. That's it. I care for you. That's why I am asking these questions. If you don't care for yourself, nobody can help you. If there is any doubt that you have in the previous chapter, anything you want a clarification from me, you can always come back to me. I can always clarify. Anything else you want to say? Nothing to say? Huh?
You will upload these videos as usual, right, ma'am?
Tell. Which one? I didn't get you. I didn't get you. I didn't hear you. Can you just type otherwise? You will upload these videos as usual. Yeah. Only chapter 28 I have not uploaded because I didn't teach you that chapter. But from here I'll be uploading as usual because now it's back to the normalcy. I was not well. Now I'm okay. So we are back. So Kaladhar, did you attend those classes? Is everything clear for you? Okay, I'm just hoping that everything is clear. In any case, if anyone has any doubt, you can always ask me. Okay, so I'm just stopping the sharing. Okay, you can leave now.
Thank you, ma'am.